Thanks a lot for having me. I'm Tom. This is joint work with my co-authors Aditya and Jordan. I'm a climate economist at the University of Exeter. As I'm sure you're aware, there's a very large literature that aims to translate temperature projections, such as those produced by CMIP, into estimates of the economic costs of climate change. And usually when people do this, they have some kind of economic model. And economic models, you can think of them as being made up of kind of two components. So if we think of here of the total damages from a change in temperature on the left-hand side, we can think about breaking that down into the direct damages that are caused by a change in temperature, and also changes in the way people behave, so adaptation. Maybe there's trade and migration patterns could change. Now, another thing I'm sure you're all aware is there's a lot of uncertainty about how much temperatures will change. So even on a conditional on a given emissions pathway, the CMIP models disagree a lot about how much warming there will be. And they disagree geographically as well. So there's a lot of variation in certain high latitude countries, for example, but there's a lot of variation throughout the world. So just a few examples of here. This is the RCP 4.5. Just plotting a time series here of the different CMIP model temperature projections in the first panel for some kind of weighted average for the whole world, and then for three different countries. You can see a really big spread at the end of century, and a much bigger spread for certain countries. So, for example, a much bigger spread for Russia than from Nigeria. So in this paper, what we want to really think about is how does uncertainty in temperature projections translate into uncertainty in the economic costs of climate change? And just to think about this in a very simple geometric way to start with, on the x-axis here, think about the change in temperature, and there's some uncertainty in there. And on the y-axis, we have the kind of corresponding change in economic welfare. And imagine for a second that the economic model was entirely linear. In that case, then a unit change in uncertainty would translate directly into a unit change in uncertainty about welfare loss. But from decades of economic research, we know that damages from changes in temperature are likely extremely nonlinear. And in that case, the welfare spread could be amplified. So a unit change in uncertainty about temperature would not necessarily translate into a unit change in welfare uncertainty. And at the same time, trade and adaptation could amplify or dampen the economic response to climate change. And how much it does that is a kind of empirical question at the country level. So in this paper, what we do is we study how adaptation forces filter climate risk into welfare risk across time and across space. And in order to do that, we develop a dynamic spatial general equilibrium model of the world economy. We estimate a dynamic damage function that links changes in temperatures to changes in welfare, and we account for adaptation and for spillovers. And then we develop some analytic tools that allow us to decompose for how shocks in temperatures translate into shocks into welfare uncertainty according to both migration and trade and direct damages. So a kind of very quick summary of the findings. We find that climate risk is very, very large. We find that welfare uncertainty is not entirely predicted by warming uncertainty. So it's not just the countries that have a lot of warming uncertainty that have a lot of welfare uncertainty. The structure of the economic model really matters as well. So where do people trade? Where do people migrate? How nonlinear are the damages in different places? We find that in general, the ability to trade and to migrate ensures against damages. So welfare variance falls for all countries in our sample, all countries in our analysis, when we allow them to trade and to migrate relative to a world in which trade and migration don't exist. Importantly, we find that these adaptation mechanisms, which are migration and trade in this model, ensure against the really bad climate outcomes. And they mean that in those situations, damages are not quite as bad as they could have been. And we kind of do an analysis of who benefits from those adaptation mechanisms and find that, perhaps unsurprisingly, countries that are open to trade get the most benefits. So a kind of really quick discussion of the methods. So there's kind of two key parts here, the data that we constructed and the economic model that we use. I'll go through each of those really quickly. And there's two parts of the data. There's the kind of CMIP temperature projections that we use, and then the country level trade, population, and GDP data that we use to calibrate our economic model. For the CMIP temperature projections data, what we need for this project is probability distributions of country level changes in temperature under a given emissions scenario at the end of century. And the kind of issue is that the CMIP 6 ensemble is not designed to represent a probability distribution. Instead, it's a kind of collection of models with different structures. And so rather than just using this raw distribution in order to think about the end of century distribution of possible climate futures, we instead reweight this CMIP 6 ensemble to match the distribution of like a simple climate model, which is meant to be probabilistic. So that's the kind of first data set that we use. We also need to calibrate our economic model, and we do that using GDP per capita and population data for most of the world's countries between 1960 and 2019. We use historic temperatures, bilateral trade data, and bilateral migration data. I think all of this data has been used before. So that's the data that we use. I'm going to give a few details on the economic model now. We kind of see there being three stages to the economic modeling. Firstly, we have to kind of estimate the direct damages from changes in weather that are implied by changes in climate. But we also want to account for how trade and migration might mitigate or amplify for certain countries these direct damages. And to do that, we develop a dynamic spatial equilibrium model that allows for trade and migration. And finally, we develop some new analytic tools that allow us to decompose variance in welfare changes according to the different model components. So go through each of those components really quickly, one at a time. For the direct damages estimation, we get estimates of country level productivity by inverting our spatial equilibrium model. And then we estimate a causal model that allows us to identify the causal effect of changes in weather on changes in productivity. We specify that the impacts of a change in weather they're persistent but not permanent, so they take 10 years to unfold, and we allow them to be nonlinear. And when we estimate the model, we find very strong impacts, and this is very consistent with previous research that finds a kind of inverted U-shape relationship between temperature and productivity. And just to look at this figure, what we find, and again, very consistent with previous literature, is that for cold countries, hot weather could be beneficial to economic growth. There's a kind of optimum temperature of roughly between 10 and 15 degrees, for which changes in average temperature don't have a large effect on economic growth. And then for really hot countries such as Nigeria, there's a very large effect of temperature on economic growth. So that first panel here on the top kind of shows the estimated response function, and the bottom shows projected damages from a change in temperature across these different CMIP models for those three countries. So now we have these estimates of the direct damages, but we also want to allow countries in our model to adapt by having more trade and migration in response to damages from climate change. And in order to do that, we build a dynamic spatial general equilibrium model. So what this does is it takes in inputs such as baseline productivities, where people live and how much it costs to trade and migrate with different regions, and then specifies a set of equilibrium conditions, which says that people move to where they get the highest utility, people trade in order to get the highest profits, and wages and prices adjust in order to make sure that all markets clear. Using these equilibrium conditions, we can get estimates of the welfare in each country and in each period, given the inputs that were put into the model. To assess the impacts of climate change, we consider the impacts of a climate forcing. A climate forcing leads to direct damages that shock the inputs. That leads to a new equilibrium and then a different estimate of welfare in each country. And then the impact of climate change is just comparing model runs with and without the climate forcing. Finally, and this is a kind of analytic contribution of this paper, we develop a method to linearize this economic model into different components, so we can see the contribution of the different components of this model to changes in welfare. We use this linearization to compute the variance of welfare losses across CMIP draws and to attribute each country's risk to the three channels that we're interested in here, so direct damages, trade, and migration. Okay, now on to results. So first thing I'm just going to show you is estimates of the mean impact of climate change on economic welfare by 2095 under an RCP 4.5 scenario. And you can kind of think of this as the difference in welfare between a world in which the climate evolves according to RCP 4.5 versus a world in which the climate is stationary at its current level. And we find really big welfare impacts for certain countries, and especially those in sub-Saharan Africa and in other countries near the equator. And again, this has been found many times before, and our numbers are roughly in line with others in this literature that use similar methods. However, there's large uncertainty associated with these estimates. And so here what I'm considering is just uncertainty associated with future temperature projections. And here I'm plotting for each country their expected damages from climate change, which are the values from this map. But I'm also plotting uncertainty bands across the distribution of possible climate futures in 2095 as well. And we can see there's really big uncertainty for a lot of these countries. And when we kind of, rather than plotting this as error bars, we can also think about this as probability density functions here instead. And what I'm plotting here is just for a few countries showing the distribution across these different CMIP projections of the welfare change due to climate change. And you can see for these kind of hot countries here, really big negative damages, and also the possibility of really big tail outcomes as well. The reason that there's two distributions shown on each plot is the red distribution here is showing the impacts of climate change from a model run in which we're not allowing countries to trade or to migrate, whereas the blue one is allowing the full response, so allowing for adaptation as well. And you can see, especially for a small economy or for a very hot economy, general equilibrium mechanisms such as trade and migration can imply insurance against those really bad outcomes. And yeah, but this is just a kind of another way of seeing that. On the x-axis here, I'm plotting the impact of trade and migration on the mean damages, and those in general reduce damages for each country. But on the y-axis here, I'm plotting the impact of trade and migration on the 99th percentile of damages, and that is affected more than the mean as the tail shrinks. So kind of interestingly, and this is, I guess, why the economic structure is important, is that if you look at where the climate is most uncertain, that's generally the high latitudes where there's a lot of uncertainty about future warming. That is not where there is the most uncertainty about welfare that is caused by that climate uncertainty. And the reason is the economic model filters that risk, and it's places that are more vulnerable, that have more uncertainty, or less able to trade and to migrate. When we break down the impacts according to trade and migration, we find that trade and migration play roughly similar roles in mitigating the impacts of climate change. And when we find which economies are most insured by trade and migration, we find that it's really the key mechanism in this model is how open are you to trade? So how able are you to substitute production to other countries? How able are you to change their production patterns in response to a climate shock? So on to the conclusions, the kind of implications of the analysis that we've done so far. I think one thing that we've kind of found in this project is that a lot of the climate impact economic estimates kind of focus on mean damages. That's obviously very important, but the possibility of tail outcomes is really important. And when we're thinking about the mitigating effects of trade and migration, those mitigating effects might come more onto the tail risk than they do onto the mean damages. We find that there's an important insurance value in openness against reducing the likelihood of the really bad events. We find that climate risk inequality actually compounds income inequality. So the countries that are most likely to be extremely damaged by climate change are often the ones where the tail risk is most reduced by integration. This paper is definitely not done. We're kind of almost just getting started, really. And the kind of next steps that we're really interested in considering are we'd like to think about the impacts of different trade and migration policies on uncertainty about climate impacts. And we'd also like to think about what drives uncertainty in the climate and try and kind of project country level welfare risk onto different climate channels. So uncertainty about global warming, the low frequency drivers versus on the higher frequency drivers. So yeah, that's it. That's all I had to say. Thanks a lot.
Thanks, Tom. That's really interesting. Has anyone got any questions? And put your hand up if you've got a question. In the meantime, I'll just ask one. The first thing that comes to mind with me is I would obviously think, like thinking about, say, a country like Nicaragua, somewhere in Central America that's already seen impacts of climate, and people migrate, they leave because they can't, say, grow crops, or they can't grow a cash crop or whatever it is that they normally make their living from. And then they migrate north, try to go to North America. But then it's kind of a bit difficult for me to understand, but you're sort of saying that if people migrate as a hedge against climate risk, the country that they migrate from is still better off. Is it because they're sending back remittances? Is that part of the thing? Because I think the other way around, that if all the people who are of working age and productivity leave a country, then the economy of that country should go down, or
no, it's
maybe I've got that wrong.
No, that's a great point. And there's really complicated effects, right? Both on the sending and the leaving economy. I guess in this model, we're kind of thinking about the experience of the people that were able to migrate as well, right? And guessing that if they chose to migrate in response to the shock, that must have been a good option for them, or something that they would have wanted to do. But yeah, the impact on receiving countries, on the sending countries, is really important as well, right? And this could lead to more inequality. So that's definitely something that we want to analyze. It's a great point.
Okay, thank you. Ala's got a question again.
Yeah. Hi, thanks, Tom. Couple of thoughts / questions. So obviously CMIP 7 will be mission driven. Would it make sense for you to use the same population and GDP data as the underlying CMIP 7 runs? I don't know if that would make any difference, best. But for me, perhaps this would be more internally consistent. And then on the economic model, I'm assuming when it's come to trade, you have perfect substitution across all different regions of the world.
We definitely have that kind of simplifying thing, right? That you kind of have to have these macro scale models. But yeah, it's a weakness for sure. And there has been some work in economics that's kind of relaxed that, but then you can't do certain other things. So it's kind of trade-off of what can you put in the model.
And then third final question. So obviously you have linear terms. Have you explored, or is there in the literature work using non-linear terms, especially when it's come to migration? And one thing that comes to mind is immobility. So when climate impacts are so severe, you're not even mobile at some point.
No, some of my other research is on exactly that, and it's in practice, it's a really important point. That's not currently in this model, and I think we need to bring that in for future versions of it. Thanks for the suggestions.
Okay, thank you, Tom.